Mm, let me record the lecture. Okay, yeah. All right, let's continue with what we had before. So what we were doing was we were trying to do nonlinear systems. And we say, well, it's too hard to solve them in general. But at least we can talk about how to do the equilibriums. So we can still set it to be 0 to find the equilibriums. Once you have find the equilibrium, the next thing to do is try to determine if it's a sink, if it's a source, or if it's a saddle. We can't do that for nonlinear, but we can do it for linear. So when we see a nonlinear system, we basically just change it to be a linear system at that point. And we basically change it to be u prime equals ju. Okay, where j is Jacobian. We have done multiple times for examples. And once you plug in the equilibrium, this Jacobian matrix is really a matrix. There's no x, there's no y. It's all constant, okay, because you plug in x0 and y0. Okay. Finally, we talk about some system where the linearization fail. We only have two cases. That's when you have a linear system and you have a nonlinear system. Usually, they're pretty similar to each other when you go to the equilibrium, but pretty similar doesn't mean that they're the same. Okay, so if you really want them to have the same behavior, you better make sure that a small disturbance, a small difference won't change the behavior when you change from nonlinear to linear. And then we find there are two fragile systems. The first one is when lambda equals 0. The second one is when you have a center where the real part, a plus bi, really is just 0 plus bi, which give you a very fragile center. If this part is a little bit bigger than 0, you have a spiral away. And if this is a little bit less than 0, you have a spiral sink. Okay. Then the small difference between the nonlinear and the linear may give you totally different result when you have those kind of very, very subtle balanced cases. Every other cases, if you have a plus 2, you change that into 1.99, 2.01, really doesn't change the behavior at all. Okay, so you're all set. As long as you watch for these two cases. That's the two things we talk about. And then we have a leftover, which is roughly the, how do I write it down? The pendulum, simple pendulum. Okay, example, just for illustrations. Okay, so we have a pendulum attached by a stick. We name this to be theta, and we only worry about the balance of force in the tangent line. So what we have is m theta prime prime, which is basically ma times l, of course, and then equals negative g sine theta. So g sine theta give you the force. That's g sine theta. Okay, theta prime times l give you the acceleration, because you have the angular acceleration and then you times the radius, that's going to become linear acceleration. So this is the classic F equals ma case. That will be the differential equation that this pendulum satisfies. Now use our old trick. Let theta prime equals omega. Okay, then what we have is theta prime equals omega, and omega prime, there's m here. Okay, and we better just delete this m once you finish. And omega prime, which is nothing but negative g sine theta over L. Sounds good? That's the system. Now, can you find the equilibrium? Well, equilibrium is omega equals 0 and theta, sine theta equals 0, which give you theta equals n pi. Your G is a constant. Your L is a constant, so there's nothing to do there. What does it mean? It basically means if you have a pendulum, the only part that your pendulum will stay as equilibrium and never changes will be the following two cases. This is theta equals 0 and omega equal to 0. That means you actually go to the bottom, okay, of the swing, and you don't have any omega, which is theta prime. That means your theta doesn't change anymore. That is a balance you have. Okay, of course, this is not 0. Let's make it more careful. That's omega equals 0 and theta equals 2n pi. Okay. Another balance you can imagine is going to be this, where you actually, the whole pendulum is above, and right above is 180 degree for your theta. So theta equals n pi. Actually, don't do that. 2n plus 1 pi, which means theta equals pi, 3 pi, or 5 pi, which are all the odd pi's, and your omega equal to 0. And I mean, of course, this makes sense, right? You have done this before. You just hold a stick, you have some plate, and you just balance them. And if the balance is just right, nothing is going to actually stand still. Okay. That's the only two equilibriums you have. So you will never have a case where suddenly this one just stop here, because gravity will actually start pushing it. Okay, so this one never stopped there. Only these two cases. Sounds good? Now let's try to see, we have two equilibriums. What is the type? Do we have a sink there? Do we have a source there? Okay. Now let's just linearization. Okay, before we have partial f, partial x, just to make sure that this time you have partial f, partial theta, and partial omega, partial g, partial theta, partial g, partial omega. That gives you f doesn't have theta inside, so this is 0. This is going to be 1 if you take with respect to omega. Now, if you think about g, what I mean g here is basically the second equation. So you take the derivative with respect to omega, you get 0. With respect to theta, you have negative g over L cosine theta. That's your linearization. Now all you need to do is just try to calculate your Jacobian at the first equilibrium. So let's put it in 0, theta equals 2n pi. Okay. This implies your Jacobian is going to be this. Cosine 2n pi, that is cosine 0. This is going to give you negative g over L. And if you plug in 0, theta equals 2n plus 1 pi, you find j equals 0, 1, 0. Cosine pi, cosine 3 pi, that's going to give you negative 1. So you can see they have different linearizations. Okay, one with a negative, one without a negative. Depending on your cosine theta is 1 or negative 1. Now go ahead and try to find the eigenvalue of each and try to see which one is a sink, which one is a source or saddle. This is the first one on the square. Partial f partial theta 0, partial f partial omega 1, partial f partial theta negative g cosine, no problem. Okay. Theta omega prime equals negative g over L sine theta, no problem. Okay. Mm-hmm. 2n pi, 2 plus 1 pi, no problem. Mm-hmm. If you get the same thing, did I get the right number? Looks right to me. Okay. Then this is going to be a center. Okay. And then this one, what I wrote here is going to be a saddle. Sounds good? All right. So what do we have is this one is going to be equilibrium, but it's only going to be a center. That means anything a little bit away from this one will stay away from it, but back and forth and back and forth and back and forth, because in the theta omega plane, you actually have something like this, which matches what we expect for this equilibrium. If you're a little bit away from it, you will just stay close to it, but going back and forth and just keep doing things like that. You will never stop. Okay. However, for this one, what you have is you have a saddle. Okay. That means if you're going away a little bit from it, what you would do is you would leave this one forever. Kind of makes sense here. So if you're a little bit away from this fragile balance, you will actually just go to the other equilibrium. You will never come back again. Okay, so in this way, we can call the first equilibrium pretty stable, and the second one is not stable. Okay, so that's just a simple example to show you. In real life, this one actually, give you some directions of how to do things in real life. Sounds good? What we assume here is we do have the conservation of energy. We don't lose any energy. Okay. You can go back and think about in which situation, Because eventually the pendulum will just shake, 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 and eventually stop at here, right? Because you lose energy. Okay? Think about how you set up a system like that. Once you set it up, you think about how do you find the equilibrium of that. Then it's very easy for you to see. Once you add something very similar to the friction, the center here will become a sink. Because eventually, if you're a little bit away from it, eventually come back and stop there. Okay? For now, we assume that no loss of energy, but eventually you will have loss of energy. So this one will become a sink. And this one, it's already a saddle. Adding a little bit thing, it's either a saddle or a source, so it will still be unstable. All right, that's all we have. So the equilibrium analysis is done. Basically, you just change it to a linear system. Sometimes you may fail. Just watch for those kind of cases. Now let's look at 4.2 qualitative analysis. Is that really the title? Wow. It is actually called qualitative analysis. Pretty sad, but yeah, that's the name. Okay. So what do we want to do? Well, same thing we did with linear systems. If you know it's this, it's you know this. That's the beauty about linear systems, right? Once you know these two, actually, the two straight line naturally divide your whole thing into 4 quadrants. Once you know what happens on the axis, you actually know what happens at the quadrant. For example, this one will be this. Okay. So even if you only know the behavior on the straight line solution, you actually know everything, because every trend need to follow which quadrant they belongs to. Now we move to nonlinear case. Number one, they're not straight anymore, so it's very possible that your two curves will not be straight line solution, but following a nonlinear curve. And they may not just intersect themselves for once, they may intersect themselves for multiple times. So you don't have 4 quadrants anymore. Instead, you may have a lot of quadrants, or we don't call it quadrant anymore, we just call them regions. Now the question simply becomes, okay, if you have on this one, you have a center, and it's going like that. You found this one, you have a center here, which is going like, I don't know that. How do you determine on each region how the solution is going to flow? And from here, you can see it's nothing but just a more complicated case for this. You have more regions, not just 4, and maybe you want to be a little bit careful of how you construct those kind of curves. But either way, you have a lot of regions, and in each region, you know how the solution is going to behave. Maybe go to the northwest, right? Maybe go to the east, southeast. Okay, maybe just going parallel, whatever. That's what we will try to do next. And this idea is called Knocklane. Still, let's take an example. The same example we had before. X times y, and the y prime equals 3y, 1 minus 3y over 3. Okay, minus 2xy. All right. So what do you mean by knockline? You have 2 knocklines. You have the x knockline, which simply means x prime equals 0, or more precisely, fxy equals 0. You have the y knockline, which is y prime equals 0, okay, which is gxy equals 0. All right. Then take this example. What do you mean by x knockline? That's 2x 1 minus x over 2 minus xy equals 0, okay, which is x 2 minus x minus y equals 0. Okay. So your x knuckling, x equal to 0, or y equals, this one equals 0. So y equals 2 minus x. Can you draw them? Well, this line here. This line here. What's special about it? On this red line, on these two red lines, your x prime is going to be 0. That means your x does not change. Your x stay constant. Your dx is 0. Then all your flow will look like this. Because you don't have any x component, right? You're just pointing exactly up or down. That's what x knuckling does. Similarly, you have the y knuckling. 3y. 3y, 1 minus y over 3 minus 2xy. 3 minus y. 3 minus y. Where is it? Minus 2x equals 0. So your y knuckling is going to be y equals 0 and y equals negative 2x plus 3. All right, what does it do? Why is this? Plug in 0, I have 3, plugging roughly this. And on these two lines, all your y component is going to be 0. So your vector field will be horizontal. Does everything make sense? All right. If that makes sense, number one, we got some nice properties on these lines. We have everything is horizontal or vertical, so that's great. Moreover, of course, this one naturally divides the whole plane into several regions. For example, for this one, it becomes region 1, region 2, region 3, and region 4. Okay. On each region, you're not going to have 0 anymore for your x, but you're going to have a positive x or negative x. Good so far? So you can actually write them down. It's not hard to see. On this part, y is bigger than 2 minus x. That means 2 minus x minus y is going to be less than 0. So here, everything goes to the left if it's above this. Okay, if it's below this, you can easily check it, everything goes to the right. You have other places because they naturally divide everything, but for now, let's just focus on everything that is in the first quadrant. Okay, otherwise it takes too much time to write everything down. Similarly, for this one, you can actually check. Again, only the first quadrant. You have a line, which is y equals negative 2x plus 3. So everything here will be y bigger than negative 2x plus 3. That gives you 3 minus y minus 2x is less than 0. So everything above actually goes down, and everything down goes above. Sounds good? Okay. Now what we can do? We can put these two lines together. You can draw them in the same plane, right? And let's only focus on quadrant 1. I don't want to deal with too many regions. Together in quadrant 1, this is what we have. Now it's time to test my drawing. Okay, I would take this one to be my, oh, too bad. Please. Okay, this black one is going to be the X now line. Not going. Now need the Y. That is going to be at 3. And 2 over 3, 1.5. Y. Not going. Moreover, this one should be blue. Okay. This one should be red. Okay. Let's also write all the arrows there. So above this black line, you have a left, and below it, you have a right. Okay. Above this blue line, you have a going down, and below the blue line, you have a going up. Sounds good? Let's try to get all the information. Number 1, you have those kind of lines with different colors representing different knock line. Okay. Where the two different color line intersect should be where your x knock line and y knock line intersect is where your x prime and y prime both equal to 0, right? That should be where the equilibriums are. So the equilibriums is where these two lines intersect. I don't want to draw too much. Okay, that would confuse me. So let's just draw it. You get the idea, and then we erase it. Okay, you're looking for where the, shit, did I use black? I use black, so this one should be black. Why do I want to use black? Let's use red. Okay, to make it more clear. Okay, so where the red and blue intersect, that will be this location, this location, this location, and this location. Okay, where do they intersect? That's where the x prime and y prime both be 0. That's where the 4 equilibriums are. No, I need a different color. I use the blue. Okay, I can use green, I guess. Okay, that's the equilibriums. Now let's try to draw the null line. For X null line, everything is vertical up for the red. Vertical, sorry, not vertical up. Okay, that's everything on the red line. But now, if you think about it, vertical, you still have two choices, vertical going up and vertical going down, right? What do you have really depends on the relationship with the blue line. Now with the blue arrow, you know, if it's above, you should have going down, so. And everything here should be going up. I know it's kind of confusing, but try your best to only see the blue line. Anything below the blue line goes up. Anything above the blue line actually goes down. And we're only talking about the ones on the red line, which are purely vertical up or down. All right. Now everything on the blue line, like we said before, it's a y-inauc line. It should be horizontal. Horizontal, you still have two choices, left and right. Okay. To determine that, now you need to throw away the blue line, only look at the green arrows. And this time you want to look at the red line. So anything below the red line goes to the right. And anything above goes to the left. Sounds good? Finally, you can do the same thing. I will just roughly do it. Okay. Now this one is vertical up, vertical down, vertical down, vertical down, vertical up, vertical up, vertical up. Blue. I need to use blue. I look at red. Below the red is going to the right. Okay, that's roughly what I can do. Yes. Okay. Good so far? Now, take a look. What's going to happen to all these solutions? Well, do you see you have, in quadrant 1, you have 4 regions. This region here. This region here. This region here. Shit, this is the best I can do. And this region here. Okay. Now, how does your solution behave? Where does your solution end? Really depends on where do you start with. Do you start in region A? Do you start in region B? Do you start in region C? And do you start in region D? Okay. Now think about what happens with region A. Well, if you're inside, what you should do is you should actually follow all the arrows, right? If you go to this boundary, what happened? You just keep going and you go into region B, right? If you hit this boundary, what do? You actually keep going, you go into region D. And if you hit this boundary, what do? You just keep going up. Again, you go into region B. So from here, you can see anything that's done from region A leaves region A. To B or D. What happens with region B if you start from region B? Can you leave the region? Well, what's your choice? You can either flow until you hit this boundary. What will happen? The flow will push you back because everything on the boundary is going back to B. Makes sense here? So you cannot leave it through the blue line. Fine. What about if I try to leave it with the red line here? I go here, this way. What's going to happen? The whole thing is actually going to push me back. Good so far? So I cannot leave through the blue boundary. I cannot leave through the red boundary. Okay. What happens if I just go to this boundary? Then I got sucked in on this boundary and all the way to this equilibrium. Still okay here? Okay, so what happens with region B? Well, stays in region B. Okay, and eventually got sucked up to the equilibrium, 3, 0. No, 0, 3. Does it make sense here? Can you do the same thing for C and D? If you start from C, what will happen? Well, number one, you go to the left, you go down. Right? That's what the arrow tells you. And eventually you hit the boundaries. You hit the blue boundary, you go into region D. You hit the red boundary first, you go into region D. Good so far? So it's very similar to A. C leaves region C to B and D. Which way you go really depends on which boundary do you hit. Do you need, if you hit this boundary, you go to B. If you hit this boundary, you go into D. Yes. Finally, for region D, I think you can see you cannot leave through the red, it pushes you down. You cannot leave through the blue, it pushes you to the right. So it stays in region D. And eventually got sucked in. If you think about it, it hit the blue line eventually, it got sucked in into 2, 0. Let me make sure this is 2. This is 2, and that is 3. So, all right. Does it make sense to everybody? Okay. We didn't discuss what happens to the left half if it's not in quadrant 1 because we're talking about the population here. You never have a negative population. Okay, but in real life, of course, you can start analyzing, different kind of things if negative number makes sense. It's just a lot of regions for you to think about. If you have 3 species, you're going to have a 3-dimensional graph. You have X, Y, and Z. Okay. If you set them to be 0, it's very possible you have a whole plane. On this plane, everything is actually the Z component is 0. Right? You have a surface, the Z component is 0, so you have something purely horizontal, right? So you have all those kind of knock links again, but it won't be knock link, it will be knock plane in 3 dimension. Okay, but it's the same idea. You just cut the whole space into multiple small subregions, and you know what happens with each subregion. Basically, you just talk about, do they stay in? If you stay inside, do you stay in, or do you actually comes out? Okay, so that's one way to do qualitative analysis for nonlinear systems. That's roughly it. I don't think there's anything else I need to talk about here. Let's try to see the graph. Oh, Andrew.
Yeah, I'm just wondering. So it kind of seems like 2, 0 is a sink, and 0, 3 is also a sink. But if you were in quadrant C and you landed kind of like at the intersection of the 2 lines, would you stay at that equilibrium, or would you go to one side?
Give me a second. That's a very good question. Let's go back to this. So I understand what you're trying to say. Okay. Here. If I remember correctly, you were asking if you just happen to hit this one, right? Okay. Let's try to analyze it. I wish I could make it bigger. I will try my best. I will erase this after this. Can you see on this direction, the arrow should be this way? Can you see it's this way? Can you see it's this way? Make sense here? So it's not a sink. Can you see that? It's actually going to be a saddle. On this direction, it's going to be a sink. On this direction, it's going to be a source. So that's actually a saddle. Do you remember how we did the linearization here? We did a linearization. We find 1, 1 is actually not a sink. It's a saddle. Shit, I can't erase it. Oh, this is good. I should draw it bigger. If you do the linearization here, what color should I use? Can you guys tell the difference between this and the red? Yes? Okay then. Because I can't tell quite. Wow, that's the best I can do. Okay, if you do the linearization here, the linearization will roughly look like this. Can you see that? And then you will have this and that for your linearization. So is it a sink or source? Really depends on your linearization. But just a very good question. Your knockling and your linearization are not the same line. Okay, knockling is purely horizontal and vertical. Okay, but when you put them together in one region, they can go all the way directly in that way. Okay, that's where actually your, your linearization should go. Okay, so if I want to tell, you want to ask this question, I can tell you firmly then, through the linearization and join all the arrows, what will happen is, this thing will go all the way to here and then go into region D. Okay, or this one will go all the way here and go into region B. Okay, and which one to go really depends on, are you a little bit up or are you a little bit down? If you're right here, then you stay there, right? But, all right, very good question. So maybe just some side topic. We didn't do them all correctly, but I mean, if you go all the way out, touch here, what did happen? You just got sucked in here, right? If you go all the way here, you just got sucked in here. Even if you go all the way over here, and then you still got sucked in here, because once you touch this line, you just follow exactly this way, right? So things like that, right? All right, okay. So that's basically, you can see this is almost like a flow, right? This is like a flow in your face plane, which is really nice and intuitive. So whatever happens to your system, really it's just like you drop one small drop or small dust into the lake and try to see where the water flow just take you. Okay, that will be how the whole thing is going to change. As long as you remember how to interpret everything, that's pretty intuitive to read. I need to change the spelling now. Okay, the system we just did, knockling like that. Okay. The blue one will be the Y, X knockling, and the red one will be the Y knockling. Okay, let's look at the X knockling. Can you see that on the blue line, your thing is basically vertical? Okay, it's vertical up if it's below the Y knockling, or it's vertical down if it's on the right, to the right of this intersection. Okay, similarly, for the red one, it's the Y knockling, which means you should be horizontal. Okay, horizontal left or horizontal right really depends on, are you above this blue line or are you below the blue line? Below, you go to the right. Above, you go to the left. Just like the way we draw it. Okay, you have region A, you have region B, region C, and region D. All of them. Now, if you start from A, what happened? Well, you just flow. You take the flow, you either draw this boundary and you keep going, and then eventually you got sucked into this equilibrium. Or you go all the way through here and you got sucked into this equilibrium. So you leave region A. What about region C? Same thing. You got all the way here, you touch this, you got sucked into this. Or you touch this, you got sucked into this. B and D, you can see, if you start in B, you never leave B. Because you cannot leave B through this red line. You go there, you got pushed back. You cannot go down even because naturally you should go up. So eventually you got into here. And the similar thing happens to this D. So if you start in D, you basically stay in D, eventually into the equilibrium. That's how we use a null-claim. Sounds good? In real life, when you do those kind of qualitative analysis, it won't give you the solution, but it roughly give you a lot of useful information about the solution. For example, will my population never go to infinity? If this is the population growth, right? Maybe you don't care too much about like actually solving the equation, but more about like, am I going to go extinct? Okay. Then you say, well, depending on which region you stay, if you stay in here, you never leave this region, but extinction actually stays here at 0, 0. You will never go extinct as long as you start there. Good so far? Okay, so that's more like a qualitative analysis. You don't care too much about how that thing happened along with the details. You just care about the final destination and roughly a trend. For example, if you start from here, you can see, number one, your X population keeps going down and your Y population keeps going down. Good so far? But don't be afraid, because once we go down, eventually your Y population is going to go up. So your X population eventually going to die out, but your Y population will stay. Sounds good? That sounds like computation, right? When you take a lot of populations inside, you just say, hey, go and compete. What's going to happen? They're going to kill each other, and both of them drop down. Good so far? Just like that. Once you drop to here, what happens? Well, after that, basically you win the computation. Starting from now, the Y population will only go up. The X population will eventually just become less and less and less because the Y already went. It's just a matter of time until all the X goes 0 and the Y actually stops at the best situation they can have. Make sense so far? Okay, so through this, you can already read the trend, even though it's not, really accurate, like how long does it take or some things like that. You need additional technology, but technique, but this is already done. Okay, of course, just to show you an example, we did a simple example to show you maybe it looks like it's still a line, but actually because it's not linear, it can be anything. For example, that's a stupid example, but if you take a system like this, no system look like this, okay? But either way, you set it to be 0. You got your X null claim is going to be a parabola, right? You got your Y null claim is going to be a parabola. So you have these two parabolas. On this blue parabola, it's a X null claim, so everything point vertical up. On the red one, everything is going to be horizontal. Good so far? You can use the same thing as we did before. You have horizontal, but horizontal right or horizontal left. It really depends on, are you above the blue or below the blue? Okay, above the blue, right. Below the blue, left. Above the blue, right. Similarly for this one, it's all vertical up, but vertical up or vertical down. It depends on, are you above or below the Y null line? Above the red, vertical up. Below the red, vertical down on the two sides. Make sense so far? Once you have all the arrows just marked down on those null planes, of course you know what happens in between. Okay, this one is going to leave. This one's going to leave through here. This one's going to go in. This one's going to leave. So everybody leaves. That's why I say no system look like this. Okay, but either way, you have two equilibriums. Okay, and this one is a source. I'm guessing this one is also a source. Not a source, a saddle. Okay, I can't tell for sure, but this one doesn't look like a sink. Sink, you should actually go up like this. Sounds good? You may even have something which intersect for multiple times. Okay, give you a lot of regions, but nonetheless, you only have several regions to worry about, which is pretty good. All right. Well, we have 5 minutes left. Let's save it for next time. Chapter 5 is basically over. We only go over those kind of simple things. Okay, 5.3, 5.4. This is the first time I'm teaching it, so I got what section I should cover from other professors. Seems like I'm going faster than them, so we may have a room for 1 or 2 weeks. I can pick any free topics I want to talk about, or we can simply just take a break. I will decide that. Meanwhile, you guys, if you have anything that you want to talk about regarding, we talked about several things. We didn't go into details, like how to do control problems, for example, right? How to do those kind of things, or discrete systems. So if you have a particular system in your mind, you just email to me and say, Dr. Chen, I want to hear more about this in physics or this in control theory. Just let me know. I will actually select the topics you guys are interested, and then go into that. The only thing left for this class is just going to be chapter 6, Laplace transform, which is like 6.1 to 6.5. By the way, speaking of that, how many of you are familiar with Fourier analysis? Okay, let's take a poll. I'm not seeing everybody's face. If you are familiar with Fourier analysis, I type it in the chat. Yeah, I'm trying to decide how much I want to go into this because the book doesn't talk about this. Okay, see in the chat box. If you're familiar with what Fourier analysis is, just click yes. If you're not, click no. That will determine if I'm going to introduce Fourier analysis or not. All right. Okay. Oh boy. Okay. On Wednesday we will start with Fourier analysis. Let's see. It's not in the book, so let's see how good or how bad a job I can do. All right. Yeah. See you on Wednesday.